Hi there. In this section, we are going to finish up chapter 4 by looking at the substitution rule. So let's get started. So we have some antiderivative formulas, but they don't tell us how to do integrals like this one, right? Because it looks like we have a product here, right? And so we don't have any way to deal with products. But there is a problem-solving strategy called introducing something extra that we can use to actually make this a solvable problem. So what we're going to introduce is a new variable, right? So we're gonna take this x variable and we're gonna move it over into a new variable called u. So if we let u be x squared plus 1, then we can compute a differential. We covered differentials in section 2.9. We can do the differential here. And that, if we treat this du and this dx as objects, like something we can manipulate algebraically, we can fiddle with those equations and get certain things to line up and match up, and then we can actually do a substitution. So in order to use that substitution, you want to rearrange it a little bit. I mean, you don't have to do this, but I think it's easier to see. Take the 2x and move it over here. Now, because we said u is x squared plus 1, when we do the substitution, this will be integral of cosine of u. And then this 2x dx, we have a name for that. We called it du. And so when we do this substitution, as soon as we replace all of these x variables with u variables, or u expressions, we now have an integral that we can do, right? So we get sine u plus c. And then all you have to do is back substitute u equals x squared plus 1 back in. So this is the answer. And this technique will be used over and over and over again, not just in this class, but in every math class you're going to take in the future, for those of you taking lots of math classes in the future. And you always want to check your answer, right? So take the derivative of this. So we can see here that this has a chain rule, right? So it's going to be cosine of x squared plus 1 times the derivative of the inside function. And we know the derivative of the inside function is 2x. And so we can see that this expression here matches this expression. So here's the approach we're going to use. We're going to kind of use the same approach we did on chain rule problems. So the integrand is the result of the chain rule. So there's an inside function and an outside function. Let me show you what that means. Here's the problem we just solved. What we could see was that because this is the result of a chain rule, we can see that there's a derivative of an outside function somewhere and a derivative of an inside function, right? That's what the chain rule tells us. So by working backwards, it tells us what that original outside function was and the original inside function. So what you want to notice is that this cosine and sine, those are part of the derivative, so they change. This derivative of the inside doesn't appear in the original problem, so it changes. The only thing that stays the same is this inside function, so that's what we have to try to find. So this is not a proof of substitution rule. The fact that we proved the chain rule proves the substitution rule. I just want to show you that working backwards, it gives you the same answer. So it's just a quick overview of what the substitution rule does. So we know from the chain rule that the derivative of the big function, we get the derivative of the outside function, the inside function stays the same, times the derivative of the inside. So if we take the integral of both sides, we're going to be able to cancel this derivative and integral on the left side. And on the right side, it just stays in this expression, right? We can't really simplify this. So this tells us that the original function is the integral of whatever we saw, whatever we witnessed, right? And we saw that in the previous problem, right? We could see, here's the derivative of the outside. The inside function doesn't change. Here's the derivative of the inside. And that's exactly what we're looking for here, right? Derivative of an outside function, inside function, derivative of an inside function. That's our goal. And so when we make the substitutions, when we say u equals the inside function, and then we compute the differential, du equals g prime of x dx, those substitutions allow us to take a more complicated problem and simplify it. So this is just the simplified version. And you can see that's actually what happened in the previous problem, right? We had the integral of cosine of u du. Well, cosine was the derivative of something, right? And you just keep working backwards until you get the answer. All right, so let's do one of these. So before we go on to the answer part, just take a second and look at it. Every substitution problem is a little bit different. I wish I could tell you that there's like some one-size-fits-all way to do it. There really isn't, which is, unfortunate, but these problems can be challenging. So we have to see three things, right? We have to see an inside function, the derivative of some outside function, and then the derivative of some inside function. We have to see those things, right? If you go back and look, right, this is what we're looking for here. And then we're going to rewrite it like this. So this x squared looks like sort of like the derivative of x cubed, or x cubed plus 5. So it makes sense to write x cubed plus 5 as the inside function, which is what we're calling g of x. Remember, there's no tried and true method that always works for this. If you make a mistake, you just have to start over and try again. All right, now we compute the differential. So that's du, that's g prime x dx. So that's 3x squared dx. But when we look at this and we try to manipulate this, we can see that this x squared, when we bring it over here to the side, it doesn't look like this, right? So whenever that happens, we have to manipulate this a little bit. And that's what it says here, right? Before we can make the substitution, everything in the integrand containing an x needs to be replaced with an expression containing u. We've already can make this substitution. This is going to be square root of u when we're ready to do it. I don't know what this is yet, because here it's 3x squared dx. Here it's just x squared dx. So we have to keep fiddling with this until it looks like that. So let's talk about how to manipulate differentials. So here's our u and our du. So what we have to do is just divide both sides by 3. As soon as we do that, now we have x squared dx, right? So look here, this x squared dx, we can now replace with 1/3 du. This square root of x cubed plus 5, x cubed plus 5 is just u, so this square root just becomes square root of u. After we've done the replacement, we simplify. I always pull constants to the front, it's a good idea. And then any powers, just use your power rules. So we can do this integral. We know the integral of u to the 1/2 du, right? It's 2/3 u to the 3/2 plus c. You don't have to show all the arithmetic. If you're still struggling going from this step to this step, show the steps, but I'm not requiring it. And then simplify and back substitute, right? So 1/3 times 2/3 is 2/9. This u to the 3/2, u is really x cubed plus 5 plus c. And of course, you can check your answer by taking the derivative. I'm not going to show it here, but you can see that it works, right? So look, you do the power rule, you get 3/2 times 2/9, right? So it's going to be 1/3 times this to the 1/2 power. Then the chain rule is going to give us a 3x squared, right? So we're going to have 1/3 times 3x squared, right? It's just going to give us x squared. So it's going to be x squared times the square root of this, which is, of course, what we have right here. So when you guys are doing one of these U-substitution problems, it's great practice to take the derivative of your answer to check it, because you're practicing the chain rule. Also, once we're all done with this lecture, if you still need more practice, go back to section 2.5 where we did the chain rule and just work all those problems backwards. It'll work, you'll see. And there's your answer. All right, so here's the overall general guidelines that we're going to use. I numbered these. I'm only showing the numbers in the first example just so you can kind of get the hang of sort of like the problem-solving method. After that, I'm not going to hold you guys to any sort of step-by-step method, but just trust me that if you're skipping steps, you're not going to get the problems right. And if you're skipping steps on a test, you don't get points anyway. All right, so determine what to assign to U. That's always the first step and sometimes the toughest step. Generally, you should find something whose differential appears as a factor in the integrand and will simplify the problem, right? That's how we did example 1. We saw that x squared dx looked like the differential of 3x, of x cubed, right? It looked like the differential of x cubed. So after you assign U, substitute U and du into the problem. You might have to manipulate some stuff. You might have to add and subtract or divide some things. Make sure all x things get replaced with U things, and don't mix terms with x and U together. I've seen people do that in the past. It gets real hairy because if you forget to switch back, your final answer is x's and u's in it, and then that's going to be wrong. And then last step, find the antiderivative in terms of U. So no matter what, we're always going to do those 3 steps. For indefinite integrals, as we saw so far, you tack on a plus c, and then you back substitute U equals g of x, and that takes U out of the expression, puts x back in. However, for definite integrals, you don't include plus c, and the values of a and b are substituted directly using g of a as the lower limit and g of b as the upper limit. Evaluate using U as the independent variable. So I put down at the bottom some formulas that you can use if it helps you remember what you're doing. So again, if here we have a to b, right? This is our like beginning integral. As soon as you get this in terms of U, you can't use a and b here anymore. You have to use g of a and g of b because U is a function of x. And that's the same as the antiderivative evaluated at g of b and g of a. So if you already know the antiderivative, you can just start at this step. If you don't know the antiderivative, start at this step. All right, let's see how to do these. So here, we have the same problem twice. So this looks similar to what we did in a previous lecture. We have the same problem twice, but this is a substitution rule problem. Let's see if a substitution rule problem looks different as an indefinite integral or a definite integral. All right, so this is part A, and again, I'm labeling the steps here, step 1 through 4, just to show you how it goes. First step, right, so let me just go back and show you. Determine what to assign to U, then substitute, then antiderivative, okay? So, you look at this, and it doesn't look like there's an inside function or an outside function. Make sure you rewrite it so that you can use your power rules. Once we're here, you can kind of see that 1 plus 2x is an inside, some sort of inside function. So that's what we should call U. then du is just 2dx. Now we look up here so we can see, all right, I can plug u in here, but this says 2dx, this only says dx. So that means divide both sides by 2. Now we can do the substitution. So 1 plus 2x is u, and then dx is 1/2 du. So here we go, do the substitution. This entire thing becomes u, this entire thing becomes that. From here, so here we did the substitution. Now you want to do the integral. All I did was just simplify it somewhat here. Again, just keep pulling the constants to the front. It's a good habit. Now I'm ready to do the antiderivative, right? So the antiderivative, so the 1/2 stays up front. U to the 2/3, so up a power. So it's u to the 1/3, divide by 1/3, which is the same as multiplying by 3. So we get 3 u to the 1/3 plus c. I went ahead and distributed, and I distributed the 3, and I plugged u back in. I replaced u equals 1 plus 2x back in the equation, right here. I just put it back in. And that's the answer. Notice the plus c. It doesn't matter what you do with c. Just when you're all done, just put a c on it. You're fine. You don't have to keep track of the steps on c. And that's our answer. Again, feel free to check your answer. When you're doing problems like this, just to make sure. All right, so what happens? So that was part A. Part B, let's go back and look at it. Part B wants us to do 0 to 13, but the same problem. So when we look at the answers here, we already did the first 3 steps, right? When we did part A. We've already done a lot of this problem so far. I don't know why they won't move. There we go. So we've already gotten it to here. But when you do a definite integral, you have to use that formula that I outlined on that page, right? So you have to evaluate this at g of 0 and g of 13. Remember, u is a function of x. So we can't just plug 13 and 0 in here because we've actually transitioned to a different function. So we have to compute that. So g of 0, so here we're just plugging it in here, right? So g of 0 is just 1 plus 2 times 0 is 1. G of 13 is 1 plus 2 times 13 is 27. So now that tells me the bounds of integration for this, right? So if you were doing the problem like all the way through and hadn't already done all the steps before, you'd have a step that looks like this somewhere, right? Where you've already made the U-substitution, and then you're ready to do the integral. Well, you have to change these limits. We've already computed this, so for our purposes, we can just start here, right? So we just need to evaluate the antiderivative. Again, we don't need the plus c because it's a definite integral. We can just evaluate this antiderivative from 1 to 27, and from here it's pretty straightforward. Who knew? That whole thing's 3. So if you had to do the whole thing all the way through, we broke it into many, many steps. The first 3 steps are basically the same. But again, step 4 with a definite integral, you have to do a lot more work. This is the way I highly recommend you do it. You're going to have a higher accuracy compared to any other methods. There might be people out there telling you to use different methods. I've seen people mix X and U. I've seen people sort of do like part A and then plug in 0 and 13. It's too much work. This is actually easier. Okay, so there's a quick review here. This is some information that was in the way early PowerPoints, the first PowerPoint set, just of review material. And I just want to go over this real quick. I'll let you guys read this. I just want to go over the calculus facts here for even and odd functions. So there's a lot of algebra facts here for even and odd functions. You can do what you will with that. For those of you moving on to more math, you're going to want to probably memorize that list. But for now, let's talk about what happens with even and odd functions in calculus. So odd functions have derivatives and antiderivatives that are even functions. Even functions have derivatives and antiderivatives that are odd functions. So before we go any farther, let's think about this. Does this make sense? So here's our list of even and odd functions. Let's see if we can see a pattern there. So for example, the derivative of sine x is cosine x. The derivative of cosine x is negative sine x. Right? So you can see how it works, right? That when you take derivatives of sine and cosine, it keeps going back and forth and back and forth. Why is that? We could prove this, unfortunately not enough time in this class, but the proof is cool. It does always work. And the other one to look at is polynomials with odd exponents and even exponents. So if you have a polynomial with only even exponents and you take a derivative, what happens to the exponents? They turn odd, right? And if you have a polynomial with odd exponents and you take a derivative, they become even. So this is actually why these things are named even and odd, is because of the polynomials. For those of you who are moving on to Calc 2, you're going to see that, well, the most famous example you're going to see is sine x and cosine x. You're going to see that you can actually write these as infinite polynomials with only odd exponents, and this one will be an infinite polynomial with only even exponents. So it's pretty cool. So that's the idea, right? That if you're trying to figure out if something is even or odd, just look at the derivative or the antiderivative, and it'll give you information about the function. The other calculus fact that we want to look at is this one here. It has to do with the areas. So the integral, so if f is an even function here, the integral from negative a to a of f of x dx is actually double the integral from 0 to a. Okay, so notice that for an even function, let's say it starts off positive, this part here is half the size of this whole thing, because they're mirror images on both sides, right? So this will actually come in handy later on when we're trying to compute something and you'd much rather plug in 0 than plug in like negative pi over 6 or something. So this is actually just a way to cut down some extra work. And then same thing here. If f is an odd function, then because it's the same on both sides, odd functions are negative on one side if they're positive on the other. So as you move away, the size is the same, but the direction is opposite. So the integral from negative a to a of any odd function is 0. All right, let's use that and do a problem. Okay, so this function is either even or odd. And if it's even, we want to just say that it's double, because look here, we have negative a to a. So if it's even, we just want to say it's double the integral of 0 to pi over 3. And if it's odd, because this is negative a and this is a, then it's 0. So that's all we have to figure out. Well, x to the 4th is even. That's a polynomial with even exponents. Sine x is odd. So what happens when you multiply an even function times an odd function? Well, it turns out it works the same way as adding odd and even numbers. Okay, so when you multiply two even functions, you get an even function. When you multiply two odd functions, you get an even function. But if you multiply one or the other, you get an odd function. So that integral is 0 because the entire thing is odd. So this is a really cool way of simplifying what might seem like really, really terrible calculations. And it comes up a bunch in other classes. Again, just let me review real quick. Let me just go back. Let me just show you that this is here. If you're not sure, there's some stuff like this on the homework. If you're not sure if something's odd or even, the list of everything you need to know is here. So here's the list of some common even and odd functions. Here's the definitions. Here are some properties, just algebra facts. Here's your calculus facts. All right, let's keep rolling. So now we're going to look at, in general, now that we've seen how to do U-substitution, what else can we do? Well, now you have to start to develop some general strategies because you'll be given a problem and not know how to solve it. This happens starting today for the rest of the semester. So this is basically the order you go in. If you look at a problem and say, I know how to do the antiderivative by just doing a derivative rule backwards, use it. That's your number one thing. So if you recognize it, use it. Second one, could the integrand be simplified or expanded so the antiderivative can be easily identified? This happens a lot when you have factored things that would be multiplication and you just distribute everything and then you get a polynomial or something, right? Or where you have like a function divided by a function and you simplify it by just bringing up the denominator into the other individual functions, right? We saw that in the previous section. Third one, substitution. You never want to do substitution first, because you might find out later that you didn't need to use it and it's a lot of work. And the last one, can symmetry be used, right? Even or odd function. All right, so that's in general how you want to do it. At this stage, I'm not going to mix up the problems for you, but I do want to show you just what a couple sort of realistic problems look like. So these calc problems can look pretty weird. And just because it looks hard doesn't make it hard. And just because it looks easy doesn't make it look easy. All right. So a problem can look hard and be easy, or look easy and be hard. All right, so let's jump right in. Let's do the first one. So let's make sure we understand what's going on here. So this is the integral of cosine x times sine of x. Okay, so here we have a sine sitting inside a sine, which is pretty weird. And then we have the definite integral version of that same problem. And for the last one, we have integral of 0 to 1 of x times the square root of 1 minus x. All right, let's jump right in. So what would you make u here for your u substitution? Well, the only thing that qualifies as an inside function is sine of x here, right? Because cosine of x is on the outside, this sine is on the outside. So that makes u equal to sine x. So you don't have another choice in this case. You'd have to pick that. Then we find the differential. So du is cosine x dx. Then you look at the original problem and you say, can I substitute that? Well, if you move the cosine over, it's easier to see. Again, you don't have to move it over, but it is easier to see. Here we have sine of, well, this is going to be u. Cosine x dx is exactly du, so we just substitute everything. Then you do an antiderivative with respect to u. That's just negative cosine of u plus c. And then you plug u back in, so you get negative cosine of sine x plus c. So that one looked pretty crazy. It's not too bad. Let's do the definite integral version of this, right? So we're doing the integral from 0 to pi over 2 of the same problem. Again, this is a function of x. This is going to be a number. So we can just use the definition, right? It's just the integral of f of u du. This is g of a, this is g of b, right? So this is a and this is b. So our g is our sine x, right? Or you could have started here, because we already have this. You could have started here. So sine of 0 is 0. Sine of pi over 2 is 1. So I simplified that. I already know what this antiderivative is. I just computed it here. So you can just plug that in. I factored the negative out. That's a good idea. A negative is a constant. Factor it out. Or, because if you don't, you have a bunch of weird negatives all over the place. So here we get cosine of 1 minus cosine of 0. Evaluate everything and you get 1 minus cosine of 1, which you might think can be further simplified. It cannot. This is an exact value. Cosine of 1 is just some strange irrational number. Just leave it like that. So it's 1 radian, right? So it's like that, right? So that problem looks pretty crazy, but as you can see, once you go to solve it, it works out real nice because the substitutions are nice. After this video is over, you guys, if you're still mixed up or confused about this, go back through every problem in this PowerPoint again. These are the types of problems that appear on your test, just like past exams. A lot of the problems on the exams come basically straight out of your notes, just with different numbers or slightly different appearances. These are the most important problems. All right, let's do one more. So here, our problem now is this innocent, relatively simple looking problem here. And judging by what we've done for the last, I don't know, half hour, it looks like it's going to follow the pattern of the same stuff we've been doing. So what's the inside function? Well, there's a square root, so the inside function's probably the thing inside the square root. So you got u equals 1 minus x, du is negative dx. But then you try to think about the substitution, and it doesn't work. There's nothing to substitute here. You got to be clever. So I just want to point out that this is kind of a tricky problem. We're going to have to manipulate not just the du equation. We're going to have to manipulate the u equation too. So let's look here at this, and then look down here and say, how do we get this to look like that? Well, this normally what we had seen in earlier problems was that this x and dx would appear together in the differential, but that's not what happened. So if you end up with like a rogue x or something that just won't go away, try to manipulate the u equation. Hey, I can just switch places with the u and the x. So now when I do the substitution, everywhere I see x, I'm just going to put a 1 minus u. So now I have 1 minus u, square root of u, dx, I have negative dx, so I have to manipulate that as well. So I'm going to replace that with negative du. So here, every single thing gets substituted. Notice that this is g of a, this is g of b, right? My u function is 1 minus x. So this is 1 minus 0, 1 minus 1. X becomes 1 minus u. Square root of 1 minus x becomes u to the 1/2. I'm just simplifying as I go. And dx becomes negative du. So I distributed everything and simplified. Okay, so if you go through and distribute and simplify, this is what you get. I just pulled this negative to the front. But now looking at this, this is like a backwards integral. It's got a 1 on the bottom and a 0 on the top. So remember, we have a rule that says I can make this a negative and switch these. Let's do that. Now it looks like a regular integral. Now we're ready to do the antiderivative. So u to the 1/2 becomes u to the 3/2 divided by 3/2, which is times 2/3. This becomes u to the 5/2 divided by 5/2, which is the same as times 2/5. And we've already computed the bounds of integration from 0 to 1. Plug everything in. Anything that has a 0 to a power of 0, so all these just become 0. And you get 4/15, and that's your answer. So just for the record, this is pretty average in terms of difficulty for a problem moving forward from here, where when you do derivatives, every function has a rule. When you do antiderivatives, that's not true. You have to figure the rule out as you go. And it takes a lot of practice. So if you guys need more practice, there's a whole bunch of problems in the book. The homework tutor does almost exactly the same methods that I do, so it's really good for this. And there's other stuff you can click around on in your ebook. And as always, if you guys have questions, go ahead and email me or post in the discussion forum. And until next video, I will see you guys later. Bye-bye now.